And so it's getting down toward the end now. We have the rest of this week, and then we have Monday right after this week. And just a reminder once more of this review session on Thursday. It's going to be right here. It's going to be in person, but I'm also gonna do the Zoom. I'll share a link for the Zoom meeting as well. So if you're not able to be here in person, you can join from Zoom as well. And actually, I haven't done that in this class yet. We haven't done the Zoom live thing yet. Yeah.
Are you going to record that lecture?
Yeah, I'll do that. I'll record it as well. And just think what works better for you, in person or via Zoom. If you have questions from Zoom as well, you can just type them into the chat, and I'll try to get to them. I think I shared the other day, just to have a look over your notes before the review session so we can use the time most efficiently to figure out what we need to chat about more. Final thing, Isaac and I were chatting earlier, so our final exam is on the last day of finals. And so if you have a desire to take that exam earlier, I do not have a problem with that. The one thing I ask is that you promise me that you won't discuss the exam with anyone else, of course, but if you would like to take it earlier, maybe you have an exam on the first day and then nothing else, and you want to wrap things up, just let me know. If we have a lot of people that want to take it earlier, we might just want to find a day and time when a group of us could get together. But if it's just a few people here and there, we can find a day and time that works for you, I'm sure. So anyway, if you have interest in that, let me know as soon as you decide that. Cool. Any questions or thoughts about the final exam right now? Yeah, okay. What was that? So it's Friday. What's the date? So Friday, the last day of final exam. It's on our syllabus too. Anybody have that in front of them?
It's the
20th, yeah. And is it? Do you know the time as well?
11:30 to 2.
So 11:30 to 2 on the 20th, yeah. And final exams are weird. They don't follow the same day schedule. So it's just whenever that's scheduled. And it will be in person. Someone emailed me and asked, yeah, we'll be in person, just like our other exams as well. Cool. Same format as I think I mentioned before. I recommend just kind of looking over your notes every day or every couple days if you can't do it every day. Just look over them every day of the new stuff. Right? Because the older stuff, I pick things on the midterm that I think are most important, right? So if something wasn't on the first or second midterm, I'm not going to pull it out to put on the final, right? Those midterms have the things that I thought were most important from that content. So just study your midterms. Be sure to know, what you missed. If you missed, remind yourself of what you got correct, right? If you got correct. That's your strategy for the review part. And then the recent stuff, since our second midterm, again, looking over your notes daily is strategy number one. And it doesn't, I'm not talking about, hours every day. I'm just talking about 15, 20 minutes. Look them over a little bit every day. Have your pencil, have your pen, have your highlighter in your hand. Circle stuff that you think is important. Put a note by things you want to ask questions about. And I think you all do well. We were talking earlier. I think I have 2 celebrations of knowledge that I have not updated on your Moodle page yet, on our Moodle gradebook. Just a reminder, remember your lowest 2 get dropped. If there's a blank in there, it means I had a reason you were excused for that, and it won't count against you. If you have a 0, it means I was expecting you to be there and you weren't, and you missed the celebration. What else to share? And then other thing is, remember our extra credits, right? There are still a couple more of these seminars. If you're not able to attend those seminars, if Thursdays at 12 just don't work for you at all, let me know, and we can make an arrangement. There have been a couple people in that situation. So if you can't make Thursday at 12 at all for those seminars, I don't want you to not have any access to the extra credit that everyone else has access to, so we can set something up. So, all right. Any other questions or comments? Yeah. Yes, there is. Yeah. Yep. And those, again, are all on Zoom, and it's the same link. You can get that link off of the Environmental Studies webpage or the Biology Department webpage, either one. All right. Cool stuff. Well, it's good to see y'all. I'm going to miss all of you once our classes and final exams are over. So you should stop by next semester to say hi as well, for sure. You guys, the funniest thing happened. So last week, my stream ecology class, one of my upper level classes, we went down to the Davidson River, and we had like a kind of end of semester thing. We wrote poetry on the topic of streams. It's pretty fun. But, we're outdoors. It's when, so, we took our masks off and we brought tea for everyone to have, right? And we were sitting there having some tea, and one of the students was like, wow, people's faces look really different than I imagined they would be. I was like, yeah, that's what happens when we wear masks every single day in class. We know what people's masks and their eyes and their hair looks like, and beyond that, I don't know, who knows, right? That was kind of funny. I thought that was the line of the semester. Wow, people's faces look different than I thought they would. So anyway, it is what it is. Cool. So last time we were chatting about energy use, right? And this idea that the amount of energy we use around the planet varies a lot depending on where we live. So places like North America, we on average use 4 to 5 times as much energy every day as folks in some countries in Southeast Asia, Africa, South America, even Mexico, right? So, and again, even countries that we think are sort of culturally, economically similar to us, still use a lot less energy. So there's some interesting implications there about, lifestyle and things like that. We talked about how and so this is all in the last lecture, so I'm going to fly through this, but we talked about how about 80% of our energy use as of now is fossil fuels, but that when we look at growth in the energy sector, renewables are growing at a percentage rate about 3 times that of fossil fuels. So we're mostly about fossil fuels, but renewables are growing pretty rapidly. We talked about where energy comes from, and ultimately, where do most of our energy sources come from? Even fossil fuels, where did that energy ultimately come from? Sun, yeah. So most of these coming from the sun. But then we have a couple other geothermal energy using the energy of the Earth's core, tidal energy using the gravitational attraction between the Earth and the Moon, moving those massive amounts of water back and forth. And then nuclear energy, the question was asked, and nuclear energy is kind of a whole different deal, right? It literally is relying on the breaking up of nuclei and atomic forces releasing energy when that happens. We talked about perpetually renewable energy sources. What were some of the perpetually renewable sources of energy? This is a review session for the final right here. Yeah. Say that again?
Wind energy?
Wind's definitely one, absolutely. Yep. Wind is one. What else is there? Solar was one, yep. Geothermal?
Wind and tidal.
Wind and tidal? You guys nailed them all. Okay, so all these different sources of energy we're not going to use up. No matter how much energy we get from these sources, they're going to be able to provide us the same amount the next day. Then we talked about potentially renewable sources of energy. What were some examples of this? Absolutely, good. Timber and biomass, what else?
Hydroelectric.
Hydroelectric, And then we also, we didn't put tidal in there, but that's kind of, actually, you know what? Tidal was over there. Getting confused. And then non-renewable, this is 80% of our energy, and this is the fossil fuels, really, right? So the idea is that the amount of these that we're using is so vast that there's no way that it's going to be produced at that rate. So there is some natural rate that fossil fuels are being produced. It's just we're way beyond that. And we're so far beyond that that we know, based on the amount of reserves here, that the fossil fuels we have, if we keep using them at the rates we are, coal's not going to be here in a few hundred years. Some estimates of crude oil say that we've got 60 to 70 years of crude oil left. That's not much time. Okay, so let's talk about fossil fuels in a bit more detail. So if you remember the carbon cycle back in the day, ultimately, our fossil fuels, of course, formed by plants that took up carbon from the atmosphere, right? They take CO2 out of the atmosphere through photosynthesis. And of course, the plants store energy, right? So that's what our consumers, that's what our herbivores would eat. But sometimes those plants don't decompose and they're not eaten by other things. They're stored underground. And when that happens, the energy they captured from the sun and the CO2 gets stored underground. And so, of course, we have plants in the ocean as well, floating around. We have algae, we have plankton. So the same thing happens in the ocean. Plants that are fixing carbon and using the sun's energy turn it into carbohydrate biomass. And that sinks to the bottom of the ocean. And then when that plant biomass is covered over in sediment, right, in mineral particles that cover them, over time that energy keeps getting buried and buried and buried. And then given enough time and pressure, that energy is compacted into things like coal and fossil fuels. Or coal and crude oil, they're both fossil fuels. So the fossil fuels that we use now were formed between 100 and 500 million years ago. And the Earth was a lot different then. We actually didn't have many vascular plants. You know, vascular means vascular is like your circulation, right? Like cardiovascular. So vascular plants have essentially circulation that they transport things. We didn't have those, but we had a lot of things like ferns, different kinds of bamboo-like plants. So all these plants, this is crazy, there were dragonflies living at that time that were 3 feet across. They were crazy. So at this time, right, if you look at places that have a lot of coal now, those are areas that about 100 to 500 million years ago were swamps. And so what happens in a swamp is that, if you imagine this tree here, right, it dies, it falls over into the swamp. If you've ever waded around in a swamp, what's on the bottom of a swamp? A lot of mud, a lot of muck, a lot of fine particulate matter, right? And so what happens is that that tree falls into the swamp. It gets covered over by soil particles. And when it gets covered over, then nothing can get to that tree to use its energy. And so it gets essentially isolated, right, from the food web, right? So it's isolated under sediment. And so what happens is when that plant material dies in a swamp, it'll get covered over with that sediment, and it's not going to decay very much. That energy is not going to get used up by anything else. So then there's more and more sediment over time, and of course the more sediment that settles on top of it, the more pressure it's put under, so it's compacted more and more. And then eventually, there are geological processes involved here. It gets lower and lower and lower and lower down into the soil. It gets exposed to heat as well. And so given enough pressure from that sediment on top, and then heat as well, that plant matter, over hundreds of millions of years, gets turned into coal. It gets compacted and condensed. And so I think from what I read, I think about 4,000 to 5,000 years ago was the first time that we have evidence of people burning coal. So they found this rock, right? It's like this black rock. that burned, right? They found this black rock that burned, and it burned really hot, a lot hotter than wood. So they're like, wow, because it was like condensed wood, right? It's like compacted wood, sort of. So it's very energy dense. So other fossil fuels form through the same process, right? It's about like organic plant matter that isn't able to decay, right? So it's compacted and it becomes more and more energy dense. But oil and natural gas formed when the same thing happened like out in the ocean, in what used to be the ocean, right? So as I mentioned, like when plants and animals and things die in the ocean, they settle to the bottom like in a swamp. And then again, they're covered over with sediment given enough pressure. So places where we find oil and natural gas now are areas that were oceans hundreds of millions of years ago. So it's kind of interesting to think like how these natural cycles operate over really long times, right? And how we're essentially reaping like the benefits of these natural processes hundreds of millions of years ago. So of course then when we take these fossil fuels and we burn them, we're putting all this CO2 that was captured by these plants over hundreds of millions of years back up into the atmosphere, right? And so you find oil and natural gas together generally, and so you find natural gas sitting on top of oil like in the same areas, and it's formed at higher temperatures. So that's where these fossil fuels come from, right? It's photosynthetic energy that plants have fixed, but a long time ago, of course. So coal is the most abundant fossil fuel in the world. What event was it that really started humans using coal on massive scales? Any thoughts? What historical event?
The start of industrialization?
Yeah, it was really the start of the Industrial Revolution, and largely it was the steam engine, right? The steam engine needed boiled water to run, and there was no way to heat water up more efficiently and faster than by burning coal, because it burned so much hotter than wood. And in England, where the Industrial Revolution started, coal was everywhere. Like it washed up on the beaches. Like there was just so much coal. It's kind of natural that that's kind of where the Industrial Revolution started. So just to give you a schematic of what we talked about earlier, if you imagine we're moving through time from ancient to modern, you know, we've got an ancient sort of swamp forest, then we've got our plant matter that gets, you know, buried with all the sediment, then it's compacted through time, and there's this stage of what's called peat, which is between plant matter and coal. There's a lot of peat in, is it Ireland? Some areas in the British Isles have a lot of peat. This is all pretty energy dense. But so it just makes the point. You don't need to know all these terms. I'm just making the point that given more heat and pressure, this becomes more and more condensed to get more and more, to become less matter but more energy dense. So if we look around the world at global coal reserves, you know, North America has a lot of coal. And it's important to keep that in mind. Like that's why coal was so widely used, right, in North America and in Europe, because there was a lot of it. However, our current, I kind of told you already, but our current estimate is that it would take 200 to 300 more years to use up all of the global coal reserves. Now that might seem like a long time, but does that mean that like it's going to be business as usual until all of a sudden one day somebody's like, no more coal? Is that how it's going to happen? What happens is things become more and more scarce. Prices go up, right? So, you know, it's not going to be a sudden, boom, everything's shut off. What do we do now, right? as coal becomes more scarce, it's going to become more and more expensive. And so, as we get to this time period, this doesn't mean that we're not going to feel the effects of scarcity for a few hundred more years. It means that's based on our current estimates when there won't be any more left. So how do we get at coal? There's a couple different ways that we get coal. The first is what's surface mining, or what's sometimes called strip mining. This is how we get at coal when it's in shallow deposits fairly close to the Earth's surface. So what you do is you go in and you remove all the soil, all the rock on top of that coal seam, and you take out the coal, then you just kind of keep going down and you keep excavating. So when coal is close to the surface, we get at it by strip mining, by removing what's called the overburden, is what the miners call it. You don't need to know that term, but you remove all of the overburden above the coal and get down to it. And of course, you can do this if it's shallow, right? If it's really deep, it doesn't make sense. If it's deep, then we drill tunnels down and we go at it that way. So surface mining or strip mining, because we strip off the top layer, is how we get at shallow coal deposits. Are you reading my mind? Yeah, so one of the ways that we do this is through what's called mountaintop removal. And I know I've showed you this picture before, but the Appalachian Mountains are really high in coal reserves. And so there's a lot of coal mining that goes on in places like Kentucky, West Virginia. And this is what it looks like, right? So just massive scale operation. I don't know if you can tell, this is a huge truck right here. And so explosives are used to blow away the rock down to the coal seam. You can see this kind of dark layer here. That's a coal seam there. And of course, what do you do with all this stuff that you've taken off the mountain? Well, you put it into the valley and you fill it up over here, which has this weird kind of cinder block looking kind of thing. So it's amazing technology, right? It's crazy. Like the thought and the technology that goes into doing this is amazing, right? It's an amazing act of human ingenuity to be able to do all this. So what do you think of the environmental impacts of getting coal that way? Any thoughts? What's that?
Pollution.
Definitely pollution, for sure, yeah. This is an example of water pollution. It turns out that the rock underneath the soil has a lot of sulfide minerals in it around here. So when it mixes with water, it produces sulfuric acid. And so when it's acidic, it dissolves iron in it. Sometimes you see kind of this reddish looking water coming out of places where there's pollution going on. And it's because the water is acidic and it's dissolving iron in it. So the first thing I think of is erosion. We've talked about that as a problem. When you're taking all those trees off at first, that's a problem. So runoff is going to be a real big problem. And, in West Virginia, they're having a lot of problems with keeping their streams healthy, because when it rains on these areas, the water that runs off is acidic, and the acid water goes into their trout streams, and so their species are unable to survive. And trout's a real important species. They need real clean water. So when you have drainage out of these mines, it's a problem as well. And another thing I mentioned too, just is because I'm a stream ecologist, I'm out there studying the rivers and streams, and I know how important headwater streams are. What are headwater streams? Anybody know what that means? Have I seen that term before? Headwater streams are the streams way up at higher elevations. They're the tiny little streams, the ones that come down from the springs. And they make up over 60% of the whole watershed. They're most of what's out there. And they're real important for processing nutrients, for processing energy from the ecosystem. They're super important. And so, we're burying all the streams up here in the mountains when we're storing all that overburden. This is so the law requires that after you're done with mountaintop removal, you can't just leave the site that way. You're supposed to reclaim the land is the term that's used. Like, you're supposed to make it so it can be productive again. But the bottom line is that really not much of anything can grow there. So this is a site, there's water running off of it that's acidic, and all you can really get growing there are these tiny little grasses. So this looks very different from a forest when it's done. This is a site that's not, it's actually not a great picture. I should get a better picture, but this is a site of mountaintop removal that's been, like, it's good now, like, its stuff has been planted, but it still looks nothing like a forest ecosystem, of course. Well, we're starting to learn more about the impacts on human health of mountaintop removal. So this is a map done by a group called Appalachian Voices. And this looks county by county in the southern Appalachians. So we've got West Virginia, Kentucky, Virginia, Tennessee, and of course, North Carolina over here. And these red marks are mountaintop removal coal mines. So you can see there's a lot of them, right? Like, they're a big part of the landscape out there. Well, again, like, you can imagine when you're using dynamite to, blow rocks and all these things off the land, you're putting a lot of stuff into the air. And when you look in these counties, which are some of the poorest counties in the country, deaths from respiratory disease, statistically, in the counties that have a lot of these mountaintop removal coal mine operations, are much higher than other places. So that's one of the costs of getting our energy from coal that maybe we don't think enough about, is that there are people. If you remember that article we read back in the beginning of the semester by Hopkins that talked about, do you remember the term they used to talk about places where people kind of paid the price for our resource consumption? There's a zone that Hopkins talked about that exists whenever we use resources unsustainably. He called them sacrifice zones, right? That in order for us to be able to be using all this coal, the people that live near where we're getting all this coal out are sacrificing by increased rates of, in this case, respiratory disease, right? So again, when we think about sustainability, it's not just the resource, it's people too, right? It's the effects on people. There's a similar figure looking at deaths from cancer. And similarly, there's a statistically significant relationship between rates of cancer death and location of these mountaintop removal coal mines. So again, this is something that we're just learning about now, but it's becoming clear that there's a public health cost and just like a sacrifice by the people there for us to be getting at coal in this way. Okay, so what we do with coal, how do we use coal to produce electricity?
Heat.
Say that again?
Heat.
Yeah, so we burn the coal to heat up water. We boil the water, turn it into steam, and that turns a turbine, which then generates electricity. Well, we can do the similar thing by burning natural gas. And so recently, there's been a shift, a decline in the amount of coal use, and an increase in the amount of natural gas. Now I don't know if we say the current administration or the previous administration now, but the Trump administration put several rules into effect that made it easier to mine coal. So this number has increased a little bit since the Trump administration was in power. But there had been this transition from less coal and more natural gas. So let's chat about natural gas just a bit. This is looking at US natural gas production. And you can see from the 1990s to 2010, there wasn't a whole lot of, I'm sorry, from 1990 to 2005, there wasn't a whole lot of difference. But then there's this massive increase in what's called shale gas. Right? So we can get at any of these fossil fuels in different ways. Shale gas is extracted by a process called fracking, or hydrologic fracturing. We'll talk about that in just a second. But in the beginning of the 21st century, this method of extracting gas that is contained in shale became well developed. And so starting in 2005, the amount of natural gas produced in the US started to increase, whereas it had been kind of constant for the last 15 years or so. So hydraulic fracturing is the way that we're getting at most of our natural gas now in the US. Now the way this works is that you have a layer of rock which contains natural gas. This is typically something like shale, for instance. So shale is often formed in association with fossil fuel deposits. And this can be a mile underground. But what we can do is we can drill down a mile through all these other layers of rock until we get to the layer of rock that contains natural gas. When we get to that layer, we can turn our drill bit and start going to the side. Right? And so we drill a long shaft through that gas-bearing formation. So because it's underground, it's under pressure, right? And so when we drill down to it, the gas is going to tend to come back up the hole that we've drilled. And what we do is we use a fluid, there's a fluid that gets injected down, it gets injected down into that layer, and these fluids are engineered so that methane, which is natural gas, so that methane will dissolve in it. So once we've drilled the shaft, we pump this fluid down there, the natural gas becomes dissolved in that fluid, then we pump that fluid back out and we extract the natural gas. Now it's called hydraulic fracturing because when we do this under pressure, it breaks little fractures in the rock, and that causes the gas to flow through it, to flow into it. A little note about this. So the environmental impacts of this aren't very well known really yet. We're starting to learn more. What do you think might be some of the impacts of this on the environment? Any thoughts? Mm-hmm.
In the previous class list, we talked about hydraulic fracturing, and sometimes when you put that fluid into areas where there's old fault lines, it can make those fault lines active again, so causing more earthquakes.
Yeah, thanks. And it was actually part of this cartoon, yeah. So in places like Oklahoma, they're seeing increased seismic activity because we're injecting like a liquid underground, and it can be almost like a lubricant to fault lines and make it easier for these small earthquakes to happen. So we've seen increased seismic activity, more earthquakes, basically small earthquakes, not massive ones. So we've seen increased earthquakes in some of these areas. Any other thoughts on what the environmental impacts might be? Yeah.
I know there's a phrase called faucet fires.
Yep.
From fracking, where the methane gets into municipal water supplies. When it comes out of the faucet, they can light it on fire.
Yeah, so that can happen. You'll notice here we've been drilling down past aquifers which contain water and which might be connected with water supplies. And so if there's any leaking here of what's called the casing of this drill, and we start getting methane dissolved in the aquifer, that's what this little question mark is here, right? If there's any methane leaking into that aquifer, then when the water comes out from under the pressure, for instance, at a faucet, it can be released. Yeah, I mean, there are videos there of people lighting, you know, like lighting the gas on fire that comes out of their faucets. It's pretty rare, but it has happened in a couple cases, yeah. So, and really, an even bigger concern is what all these fracking fluids might do to the aquifers. Because the crazy thing is, so fracking is the short term for hydraulic fracturing, right? These fracking fluids, because this technology was new, like every company had a different chemical that they used. And in some states, such as North Carolina, they were not required to disclose what the chemical was, because they said, well, it's an industry secret, like we can't say what chemical we're using, or like other companies will steal our secrets. And so it's kind of crazy. For a while, companies were pumping all these chemicals underground to get the natural gas out, and they weren't even required to say what the chemicals were. And so there's been quite a bit of concern about water pollution from those chemicals. It does generate a lot of wastewater. And this fluid, when it comes out, there are some operations that reuse it, but not a lot. So disposal of this fracking fluid and then wastewater that comes up from this drilling process as well is a concern. And then, of course, as with all fossil fuels, we have the overarching environmental concern of the fact that we're taking carbon that had been stored underground and putting it up in the atmosphere, right? And we know, of course, that CO2 is a greenhouse gas. But this has made natural gas a lot cheaper. In fact, for the longest time, the used to be Progress Energy, now it's Duke Energy power plant out by Lake Julian here in South Asheville. For the longest time, that was a coal-burning power plant. They've now completely transitioned over to natural gas because there's just so much more of it around now. And that's a net win for climate change, because natural gas per amount of energy puts less carbon into the atmosphere than coal. But, you know, newsflash, at some point the natural gas is not going to be so cheap anymore, right? So, anyway. Okay, so let's talk a little bit about petroleum. So petroleum often is formed in association with natural gas. And so, if y'all remember from that cartoon last time, like after World War II, again, in the United States, this is when we were building these suburbs. This is when like the culture of like driving your cars all over really took off. Starting in that time and then moving on, petroleum is the most used fuel on the planet. It's what we use for our energy more than anything else. So what we actually extract from the earth is called crude oil. And it's a mixture of a bunch of different molecules. And when oil is extracted, it's first sent to a refinery where it's essentially sorted into the different components. So jet fuel is one component. Octane, right, which we use in our cars, is another component. Kerosene is another. It's a distilling process. So crude oil contains all these different kinds of fuels. It even contains tar, which we use like for asphalt in our roads, all that kind of stuff. So in the US, right now, we use about a quarter of all the oil in the world. And you know, I think it just speaks to like our, I don't know, kind of like our transportation culture, for lack of a better term, right? That we like to drive our cars, right? And we don't use public transportation as much as some other countries. So in the U.S., we're using a lot of oil. which is a problem because we don't have a lot of the world's oil. So in 2010, we learned a lot about the environmental impacts of extracting crude oil. So we talked about how with coal, right, it's not going to all of a sudden run out, and we're going to wake up and be like, oh, no coal, sold the last piece yesterday. Like, it's not going to be that, right? There's going to be this decline in abundance, and as it gets less and less abundant, it's going to be harder to get. Well, that's what we see with crude oil. Anybody ever see what is it, Beverly Hillbillies? Is that what it is? You know, where it's like, struck oil, you know, in the backyard, this gusher of oil. That used to happen, but it doesn't anymore. The oil that's easy to get to, we've used up for the most part. So now, when we need crude oil, we need to go to places like deep water offshore, the Arctic. These places where it's hard to get at the oil, but it's now profitable because oil is becoming more scarce. So what happens when you do that? Well, this was the Deepwater Horizon. So back in 2010, this was a deep water oil drilling rig that caught on fire and exploded. And there were 3 million barrels spilled. There were 4 gallons of oil for every person in the US that were spilled as a result of this. And coated hundreds of miles of the coast with crude oil, and just a massive economic impact in the billions of dollars. They're still finding fishes like tuna in the Gulf of Mexico that have very high rates of toxins in them from this spill. I don't know if you can see, this is what it looked like from space. So this is Louisiana right here, and this massive oil slick was visible from space, right? And so just covered hundreds of miles of the coastline, cost billions of dollars to clean up, and we're sort of still facing the cost of it. So the question then, right, is like, so how long will the petroleum last? And the way that we get at that question is to look at what's called peaking oil. So the estimate that I mentioned earlier about oil running out in 70 years, that just came out recently. But our most standard estimates say that oil production will peak somewhere around 2050, and then it'll go down. But the thing is, in the US, we're not the ones that are going to be producing it. So the oil that we actually have access to is a function of how much the oil-producing countries let come onto the market. So because of that, there's this imbalance between those that are producing oil and those that are consuming oil. And so not all countries are going to be affected at the same time. I mean, Saudi Arabia can store enough oil to use it till whenever, right? But in the States, we're not going to be in that position. I realize I've had a lot of text on these slides. I see you're still waiting, so you're still writing, so I'll pause for a moment here. So if we look at what's happened in the US, our production peaked in the 1970s, right? And so we have been, our oil production has been coming down since then. Ever since the 70s, we've been producing less and less oil domestically. So anyway, so this is a prediction, and it was actually pretty close to what actually happened. And so you can see now, we're producing about, at this point, about half as much oil in the US as we used to back in the 70s. Now, if we look around the world, this is oil production from all different sources. So this is the lower 48 US states. And you can see around 1950, who was producing the most oil globally in 1950? The US was, right? The lower 48 accounted for more oil than any of these other sources. But we kind of went down from there. Whereas all these other sources, right? Russia, Europe, the Middle East, a lot more oil coming from there. Now, all of these blue colors are what's called unconventional oil. This is oil that's hard to get to. It's hard to get at. Oil from the pole, oil from deep water, what's called heavy oils. How about that in just a second? Oil that we have to boil out of sand. And so all of a sudden, come 2010, the oil is being produced everywhere else, right? And so we're having to buy it from these other places. So what we're going to notice is that, like, toward the end of the century, towards 2050, right? You'll note this projection has oil peaking in this decade, actually. But all of a sudden, this unconventional oil becomes a lot more prominent. So we import about 60% of our crude oil, basically, right now. So we really like to consume oil, but as I said, unfortunately, we don't have a lot of it. So what that looks like graphically is this. So with the US, we produce about 5 million barrels of oil per day, whereas we're consuming about 20 million barrels. Does that math work out? Based on this is saying 70. Okay, this is the, all right, that must have been updated. This is cartoon. Remember. So this is actually saying that we produce 5, consume 20, 15, 20. Yeah, so, well, yeah, so this is actually, this most recent data suggests that we're importing over 70%. Suffice to say, we're importing the majority of it. Countries like Germany and Japan are in a similar situation. But then we have other nations like Saudi Arabia and Iran that produce a lot more than they consume. So that's where the tension is, right? And that's kind of like global alliances in the 21st century, right? Like, we want to keep good relationships with countries that are producing lots of oil because we have to buy it from them, even though we may not always love what those countries are doing politically or human rights related or whatever else. So this imbalance makes us beholden to lots of these other countries. What if we could just reduce our consumption of oil, and then then these countries wouldn't all of a sudden have so much leverage, right? It's challenging. All right, so let's think a little bit about this switch from fossil fuels to renewables. First of all, I hope you've seen by now, it's not a question of, are we going to switch from fossil fuels to renewables? It's a question of when and how. Because we're going to have to, because fossil fuels are going to run out. Like, it's a finite resource, and we're using it at a faster rate than it's being produced, right? So there's no question of if we're going to or not. The question is how and what that's going to look like, right? So this is a graphic from National Geographic, and it plots global demand for fossil fuels, which is expected to increase because, oh, by the way, countries like India and China, each of which have a cool billion people on them, are developing economically. When I was in India, so my wife is from Northeast India, and we were visiting there 2007 maybe, and for the first time ever, so I was in the Peace Corps in Nepal in the 90s, right? And it was like nobody owned their own car. Like, if you wanted to go somewhere, you'd hire a car with like a driver to take you somewhere. There weren't that many cars around. But when we were there in 2007, for the first time, I saw advertisements on TV for cars. And it was all framed around this idea of like taking your family on vacation. kind of like our culture, right? So these other countries in the world with billions of people are also going toward that lifestyle. So I say all of this just to make the point that like, as these fossil fuels become more and more rare, global demand is going up. So all of a sudden, we're competing on the marketplace with countries like India and China for fossil fuels, right? Okay, so anyway, this all I really wanted, the only point I really wanted to make here is just that, you know, there's going to be this gap, right? So as our demand goes up and production goes down, there's this gap, which means that it's going to be harder to get and more expensive. And so, all right. So as oil becomes more and more expensive then, it starts to become profitable to extract it in ways that are really expensive and energy intensive. And an example of that are the tar sands in Alberta, Canada. This is what the Keystone XL pipeline is proposed to be built for. To move this crude oil from Canada down to the lower 48. So this is what an oil extraction process looks like. You can't even see the oil. It's a liquid, but you can't see it. The reason is because it's soaked in the sand here. So to get crude oil out of the sand, you know, it's not longer a case, right? To put in a pipe down and just suck it up. Great. To get crude oil out of the sand takes twice as much energy as getting it from the surface. So clearly it's more expensive. So this doesn't make sense to do when oil is cheap. Well, when oil is not cheap anymore, all of a sudden this process starts to become profitable. And then, oh, by the way, if you have a pipeline that'll take it to refineries along the Gulf Coast, well, then even better, right? But so what we have to do to get at fossil fuels in this, to get crude oil in this way, to produce 1 barrel of crude oil, so barrels are about 40 gallons, I think. That just popped into my head. You might want to double check that. I think that's what they are. So we have to do, so of course, cut down the trees because there are plants that live out here, because this stuff is below the soil, I should mention. So you got to cut down the trees. You got to remove 2 tons of peat and dirt. So all the soil on top of there, you got to remove all that. Then you got to remove 2 tons of sand. So this is for 1 barrel of crude oil we're talking about here, right? So, I mean, so you kind of start to see like where the cost comes from, right? I mean, this is not like a geyser of oil that you're just tapping into. And then you have to heat several barrels worth of water to boiling to process that sand and separate the crude oil from the sand. Which, of course, produces an awful lot of wastewater. And so the last time I checked, there are about 50 square miles of this wastewater, of ponds with this wastewater. And so this little device here, anybody know what this device is here, floating on top of one of these settling ponds? It's got a bird. First of all, that's not a real bird, that's a fake bird. It's a device that uses radar to detect when migratory birds are coming. And then it turns on this device, which makes a call like a predatory bird, like a hawk. And then this bird flaps its wings, and it's designed to scare away migratory birds, because there was at least one instance where a flock of migratory birds thought this was water and landed in it, and they all died, right? So this is kind of a pretty massive environmental liability. So about 50 square miles of settling ponds here. So this is what the Athabasca River looks like right now. This is what an area looks like after they've gone in and extracted oil from tar sands. So, so I did a little math. So it's estimated to hold 173 billion barrels of oil. Now that sounds like a lot. But I looked up the current rate of use of oil in the US, and I divided it into this number. And it turns out that it would give us enough oil to last about 20 years. So if we were to go up and do this, right? Turn this into this, we would get enough oil to keep us going for 20 more years. But then 20 years from now, we're facing the exact same problem. Meanwhile, we don't have this anymore. You know? And so really, all that we're doing as we get oil from these more and more expensive, energy-intensive, and oh, by the way, environmentally damaging, off the inevitable. So I think it's important when we think about the question of renewable energy, not to frame it in the sense of do we or don't we, right? Because we know that we are going to convert, right? It's, you know, that's not a question anymore. The only question is how long we're willing to put off the hard decisions that are going to come eventually, right? Like there's no way to run away from it. Like those decisions are going to come. Like we're going to have to make those decisions. The only question is when we make them. And really when we force us to make those decisions is going to determine largely what our environment looks like when we start to make the switch. I think I shared with y'all is, you know, so we have a course in this department, which some of y'all may be taking next semester, called Energy and Society. And it talks about a lot of this stuff. But Dr. Moorhead, who retired last year and taught that course for decades, said, you know, the renewable energy train has left the building. I mean, it's happening. Countries all over the world are switching to renewable energy. But what's happening is that the economies that are based on these fossil fuels have been in place for, it feels like a long time, y'all, but it's not. They've been in place for like 50, 60 years. That's not that long, right? So we are switching and things are happening, but the only question is what it's going to look like when we're done.